I will be telling here most from the theories perspective, not like a very observational cosmologist perspective. And I will be focusing more on the observations which can test the late time universe. And to start with, the cosmology start from the cosmological principle, which you already know from the previous talk by Chakri, that our universe is both homogeneous and isotropic in sufficiently large scale. So you have to go beyond a scale which is more than 100 megaparsec, and which is like that we call like the observable universe. And this shows you the homogeneity in this figure, and this shows you the isotropy. And the universe is the both. So the consequence of this cosmological principle there is that the physics is same at every point of the universe. So you are not at a special point. And as you know that we study, we use the theory of gravity to study our cosmos. And there are two different ways till now. The most precise way is the Newton and Einstein. And in Newton's way, mass tells gravity how to exert a force, and force tells back the mass how to accelerate. And for the Einstein way, is the mass energy tells the space-time how to curve. And the curvature tells the mass and energy how to move. And you know this is the famous Einstein equation, which Chakrit has already, I think, derived in his talk. And the first observation about our cosmos started from not from Hubble, before Hubble, but the most significant observation is from Hubble, where he was studying the recession velocity of galaxies, and he was plotting the velocity against the distance. And to his surprise, he found that as far you go in the distance, the velocity of the galaxies increase. So the farthest galaxy is moving with more velocity. And this gives the idea that our universe is not static. Our universe is expanding. And you saw about this from Chakrit talk, that this if our universe is expanding, the spectra from the galaxies will be red shifted. Because if you know from the Doppler shift, the effect of Doppler shift, when a source is going away from you, so the wavelength is stretching. So wavelength is stretching means your photon is losing energy, and you are going more towards the blue in the red in the spectra, and it is coming towards you, so your wavelength is squeezing and you like giving higher frequency. So you get your spectrum is moving towards the blue. And this is the definition of the redshift. And in 1925, Hubble measured almost 40 galaxies, and he found almost all of them are redshifted. And from this formula, if you just write when the velocity of the galaxy is much lower than the velocity of light, you can write that V is H0 into R. It's a linear relationship between the velocity and the distance. Sorry. And from there, you can actually describe that. You can justify this plot from Hubble. So this gives us the idea that the universe is expanding. And one of the consequences of this expanding universe, so I'm going a bit fast because you have it in the previous lecture. Yes. So one of the consequence of the universe is expanding today is that you can actually go back in time. When you go back in time, things are going to be contracted, yes, not expanding. So you will arrive at a point where you encounter a singularity, and that we call generally Big Bang. And this is the evolution of our universe, and it started from a Big Bang, and then you go through a inflation period, and then you have the CMB, cosmic microwave background, and then you have the dark ages. Dark ages is like this why it's called dark age is like this epoch of the universe is filled with the neutron hydrogen. So you don't have much photon left, and then suddenly the gravitational collapse happen, and then you again start to get the first generation of star, and then we move and all the structure form, and we are here. This is the current epoch, and this is like a temperature. You can see how the temperature decrease with the expansion of the universe. This is just a plot for the temperature, and this is what we call is Big Bang theory. But what interesting is that in this different epoch of the universe gives us different observation to study the universe. And this is where we have like the CMB observation. There will be like 21 centimeter, and then there will be like the large scale structure, and all different kind of observations are there, which tells us more about the evolution of the universe. And this is like a more detailed chronology of the universe. I think you already know that this is the period of inflation, 0 to minus 43 seconds. Then you get a phase transition around 0.37 seconds, and all this like the structure, when the structure form, and when the cooling started, and baryogenesis started, and all these things are very standard. So you can go to any cosmology book. This you will find. This is the standard thing. Now, according to the standard model of cosmology, what are the component of the universe? We have like 70% is called dark energy, 26% is dark matter, and 5% is ordinary matter. Ordinary matter is the matter which we are made of, and like all the stuffs you actually know. And dark matter is something like it's a very exotic kind of matter which exist, and you can actually detect them through their gravitational effect, but we don't know what are they made of. And dark energy is similar, but it is the cause for, we believe this is the cause for accelerated expansion of the universe, which I will be describing later. And we don't know exactly, and there is no consensus that what this is. So only what we know is around 5% of the total component of the universe. And this is the more detailed part, and then you have proton, neutron, electron, and neutrino, and photon. And the first three we call is non-relativistic component, and then we have the relativistic components, and these are called sometimes dark component of the universe. Do you have any question? Okay. Now, when you know the gravity is the study of geometry. So, and now when you go to study geometry, one of the thing is that you have to find the distance between the 2 points. This is the beginning of the geometry. Yeah, and in Euclidean geometry, you do it like just x2 minus x1 and y2 minus y1 square. But if you take the fact that the cosmological principle to be true, that the universe is homogeneous and isotropic, then you can show that only these three different kind of curvatures is you can get. One is the positively curved, another is negatively curved, and another is the flat universe. And if you consider these three curvatures are simple mathematical like examples that your distance calculation and different kind of identities, like this is this is the Euclid identity, the sum of three angles of a triangle is pi. But if you go to on a sphere, it will be more than pi. And if you go to a negatively curved geometry, it will be less than pi. This is just an example that depending on your geometry, these kind of relations will be changing. And we can write a distance formula which is in common form. This is in three-dimensional case is like dr square skr square d omega square, and this skr can have these three different forms. One is for the spherical symmetric, another is for flat, and this is the hyperbolic. I think every one of you know what is there. And now what we do to get the Einstein equations, that we start from the action, Einstein-Hilbert action, and we then vary it, and then after variation we will get the Einstein equation. Yes, and this T mu is the matter. So this is very standard procedure, all of you knows. And now when you use the Friedman equation, Friedman metric in the Einstein equation. So Friedman metric is the metric which gives you the homogeneous and isotropic universe, yes? And it can have three different curvatures. So when you use the Friedman metric, you will arrive at these two equations, and also you will have this third equation, which is the Bianchi identity or the continuity equation. And out of these three equations, only two of them are independent. So at a time when you are using, you should use only two of them, not three of them. And if you see it here, then you will see you have two independent equations, and there are three unknowns, rho, p, and a. So you need to find another relation which can close this system, and the another relation is called equation of state. Equation of state is that how the pressure and density of a universe is related to each other. So the common consideration there is that if we consider ideal fluid, so you can come to that that P is just proportional to rho, and for matter P is 0, and so W equal to 0. And for radiation, P is 1/3 rho, W is 1/3. And how do you know? Because if we consider in cosmological scale, we have the galaxies, and they are not colliding with each other. Yeah? So there is very less like interaction between the galaxies, so everything is co-moving, and so there is no interaction here, so you can consider normal matter to be pressureless. And for radiation, probably you have already studied this when you studied your like Bose-Einstein statistics. I think you can calculate the pressure for photons inside a box or something like that. So then you can get that the P is 1/3 rho there. This is called radiation, pressure for the radiation. And now we can actually define different background quantities for cosmological observation, and one of the way is that you can Taylor expand the scale factor around today. T0 is today, and when you do it, you get the first coefficient, we call it the Hubble parameter, and the second one you will get something like half Q0 H0 square. You have to just do a little bit mathematics, and then you get a parameter which is we call Q0, that is called the deceleration parameter. And why it is deceleration parameter? Because at the beginning there was no evidence when this parameter was defined, there was no evidence that the universe is accelerating. So it was thought that the universe is decelerating. So this parameter was named deceleration parameter. And from there you can actually recast the Friedman equations which I show you in terms of some density parameter which is called omega, capital Omega, rho by rho c. And from there you can have like a, it's very difficult, which way is this? Yes. From there you can actually write a kind of a constraint equation where the sum of all these omegas give you 1. So this is called the Friedman constraint equation. And this density parameter is dimensionless parameter. And from there you can actually, this is more explicitly, you can write the density parameter in this way. And omega r0 is the current value of the density parameter for radiation. And one of the importance of writing this in terms of omega is that you normalize this parameter. Otherwise, if you think about only any density parameter, physical density parameter, so at the very early universe, the value of those density parameters will be very, very high. But if you normalize this way, so these omegas the value can be only between 0 to 1. So it's much more easier to handle these parameters rather than directly the rho. And then you put back, take the continuity equation, and in continuity equation you put for a general fluid, and you will get a kind of how density behave with different fluids. And this will be the general relation. You can derive it from the Friedman equation. And in order to accelerate the universe, this W has to be less than minus 1/3. This is this W for the dark energy, I say. Okay, that I will be explaining next. So already I think Chen has shown you this plot, and you know the radiation actually fall off as a to the power minus 4, matter falls off as a to the power minus 3. And as you see that for the radiation is like the volume expanding, so it's 1 by V, so 1 by AQ. But for matter, for radiation is 1 by V, and as the universe is expanding, your wavelength of the photon is also stretching. So you get 1 by A, another one. So that gives you 1 extra. So radiation decay faster than the matter. And this plot is like showing this is an illustration that if you consider dark energy to be like a constant, this is not very up to the scale. So the radiation is going down and it is becoming very negligible, and this is the matter is going diluting, and now at this point the dark energy domination started for the universe. And because the rho lambda is a constant quantity, if you consider the cosmological constant model. And if you have the curvature of the universe, you could have 3 different kind of evolution of the universe. One is the k greater than 0. This is the positive curvature, and you will get a universe expand, and it reaches a maximum for the scale factor, then it actually contract. And for the flat, it expand forever. And for a negative curvature, it also expand forever, but at a higher speed compared to the flat case. Now, when this is just a revision of the background cosmology, and now once we want to understand the cosmological observation, we need to understand the cosmological distances, because the measuring distances in cosmology is very important, so that and it is very technical also when you actually measure it, and that gives you the precision data to find more details about the universe. And there are like these are the three distances. One is the co-moving distance, another is the luminosity distance, and another is the angular diameter distance. And what is the co-moving distance? Co-moving distance is just like if you consider this sheet of the paper, and there are two galaxies fixed at two coordinates, and if this is your like the origin, so the coordinate, when the universe is expanding, this coordinate for my plots is changed, but this coordinate should not change, but only the distance between 2 points, the space itself is increasing. So that distance, the coordinate distance, we call it co-moving distance. And when you multiply it with the scale factor, so you get actually the physical distance between two objects in the universe. Is there any question? No? Okay. Yeah, so that was the illustration. And how can you do it? How can you compute the co-moving distance? Like, you consider a galaxy and a photon is coming to you, and then photon follow the null geodesic. So you can consider the effort W metric, put ds square equal to 0. Yes, photon has the travel through null geodesic, and then you can like integrate it 0 to x1 and 0 to t1. Yes, so this chi-square is your co-moving distance, and this at you can write. This is from the definition of the Hubble, the definition between the redshift and the scale factor. You can write dt is dz h1 plus z. So then you put it back here, then you get this is the formula for the co-moving distance. And you can actually Taylor expand it, and you can see you can neglect the z square, yes, term if you considering very nearby universe, not high z. So then you will arrive at this relation, which is nothing but the Hubble law. Okay, it can give you the Hubble law. You get back the Hubble law at low z limit. And then another distance is the luminosity distance. Luminosity distance is like when we try to observe some luminous object in the universe, and the photons are coming from that object to us. And suppose you have this, this is the source, and this is the flux by the, this is the luminosity, and this is the flux observed by the observer. Okay, so suppose this is some galaxy or star, and then you write it, you know it, dl, so 4 pi r square into f. The flux is the amount of energy you are receiving in unit time, unit area. So you multiply it with the whole area of the sphere, and then you get the luminosity is like the energy released by that source each unit time. So this is in flat space. You can do this one, but you have to remember you are in a universe which is expanding. So the photon, when it is released from some object, and when it reached you, it will have the wavelength will be stretched, and then you have to put that in your calculation, and there will be another term is 1 plus, another 1 by z will be introduced. And you can write the dl as dc into 1 plus z. Maybe I describe in the next slide is in better way. So dl square is in terms of that luminosity by 4 pi f. And this f account for co-moving distance. So if we consider co-moving distance, this f will be, then this dl will be 4 pi dc square into 1 plus z square. And then you get dl is dc into 1 plus z. Now what you can do is, like, you can find the relation that dl is going to be, you put back the dc and you get the expression for dl. And here the expression is for the 3 of the curvature putting together. And you can, for the flat case, you have to take a omega k equal to 0 limit. You get with the flat case relation, flat case formula for the dl. And you can actually do the similar expansion, Taylor expansion of dl, and at low z you will get back the Hubble law. And how am I doing time? What's the time now? Oh, okay. So now there is another distance which is called angular diameter distance. This angular diameter distance is used to study the extended object of the universe. Now we were studying directly the distance to an object, but suppose you have an extended object, and mostly used for the CMB anisotropy and the observations from the cosmic microwave background. And the idea is very simple, and I should give this disclaimer: all these graphics are Gemini Pro. So there might be some small fine-tuning problem because I cannot tune them, but I like them the way they describe it. Yes, so you can see that this is the physical size of this galaxy along the what is called transverse to the line of sight, and then this is the distance, angular diameter distance. And you know this this relation, no? dA is r d theta. The arc is in a small angle approximation. You can write the length of the arc is d theta into the distance, and you can actually find a similar relation between that dA is dl by 1 plus z square. And the angular diameter distance, you can actually, more like detail, you can try to write the expression is dA is del x by del theta, and del x is again dA is a scale factor multiplied by this fk, and this fk is the f chi is the, I think this is the co-moving distance, and then you will arrive at this formula. Again, if you take the omega k equal to 0 limit, you will get back the angular diameter distance as in flat space time. And this is the relation between dA and dl. Yes, and but now is there any question before I move to the next? Mm-hmm.
Can you define these distances in a covariant way without referring to particular coordinates like the moving coordinates? Or if I want to frame it in a better manner,
Mm-hmm.
can you define these distances without the assumption of cosmological principle? Or cosmological principle is the prerequisite to define these discrepancies?
I think you have to, because otherwise if cosmological principle is not there, so your sense of co-moving is already gone.
Not there.
Yes. There will be no co-moving frame if you don't have cosmological principle, or we'll have it. I don't know.
I don't know.
Yes.
So basically all our measurements are based on the assumptions of cosmological principles.
Yeah, I think so. Do you have any comment on that?
Yeah, of course. Yeah, there is homogeneity and isotropy.
Yes, yes.
Distance doesn't depend on the angle, just depends on the redshift. So, yes, it's intrinsically defined. Homogeneous.
Oh, yes. Well, that's a good question. Like, I think.
Yeah.
Like maybe you were thinking about Bianchi style, Bianchi model.
Not only Bianchi is definitely something. I was thinking how much of our observations are marked by the fact that we have an inherent assumption, inherent symmetry assumption.
Yes.
Yeah, one way would be to go and study perturbations. So you go out of the homogeneity base. Second way, you study what is called the Swiss cheese background, actually. Swiss cheese. So essentially you had to go out of the idea of isotropy and homogeneity. So, but again, modeling the universe we can see actually. So essentially voids would correspond to the whole of the Swiss cheese, essentially. So you have almost homogeneous except these voids. So this would be a background itself. And then you study this kind of definition inside that background. Another way is to relax the homogeneity going to perturbations. So it means that one is the leading order term, and then you have correction to that. But yes, it's intrinsically, this is in a sense, people are doing observation in a homogeneous and isotropic universe.
So like if you assume perturbations, there will be corrections to this definition.
Sure. But as you said, like for CMB we do perturbations, and the CMB observation tell us that the background is flat. So it's like, CMB agrees with the homogeneity and isotropic.
CMB, you already are at that perturbation level.
Yes.
So what it means is that in principle you should correct whatever observation you have through perturbations.
I understand.
But this should be still a dominant contribution.
Yes.
At large scale.
Yeah, at large scale.
Because small scales.
Yes. And all the observation is not that very high Z, I think. The Z is quite still low, so we can consider this. Even you have something, but the leading order will be this, I think, as Antonio said. Yes. So now we know that currently our universe is accelerating. So the expansion rate of the universe is increasing. So this plot is not has some meaning. This age shows you the evolution of the scale factor. Here you see it's up to this age you have a negative slope of this scale factor, and then it is increasing here. So that means the universe is expanding with acceleration. The rate of the expansion is getting faster and faster day by day, and that we cannot explain with the matters or the information we have in our hand, and that is why we name it dark energy, because we don't know. This dark is that dark word is used because of our ignorance. Yes, nothing is dark. Why I say this? because few years back I was writing a proposal, and where my title was something on dark energy, and people had to translate it to Thai, and they translated literally to kind of dark magic, that dark. so, so then you have to careful. There is no dark magic here. Like people ask me why it is dark. Is it something dark magic, or there are some ghost or something? so I had to, and I had to take help of Mike to translate it to the like something Thai which doesn't go to that domain of the speculation. So that's why it is dark, because we don't know. And now I'll be focusing on these cosmological observations, which actually gives us evidence, mostly these four, that our universe is actually expanding with acceleration. This was first detected by this two supernova team, is Supernova Cosmology Project and HiJet Supernova Search Team, and they got a Nobel Prize in 2000. Do you remember? 11, no? 11, yes, for this discovery. And the first one is not directly observation, but it's a kind of theoretical evidence that the age of the universe. So you can actually, from the Friedman, this is the Friedman equation, first Friedman equation, which is the Friedman constraint equation, we say. You can calculate the age of the universe from this relation. This is just the relation when you write the scale factor in terms of the redshift and take a derivative. And you get dz by dt and a dot by at, it's become with as the Hubble. Now you can actually, if you know a functional form of this Hubble, so this Hubble is hz by h0. So this is called Ez is here. Ez is hz by h0. This is, we call it, this is the Hubble parameter at any z is scaled by the value of the Hubble parameter today. We call it the normalized Hubble parameter. And you can put, if you know how this is behaving, all these terms, the first terms gives you the evolution of the radiation. Second is matter, and the third one is cosmological constant, and the fourth one is because if you have a non-zero curvature, that's a curvature contribution. And when you put it back here, and you can actually integrate it. Now this integration is not analytically, you cannot do it. You have to actually do it in terms of numerics. And but a simple way will be, you just consider there is only matter today and the radiation, only matter and radiation. And if you calculate the age of the universe, that the age of the universe will be 8.2 to 10.2, depending on the value of the matter and the radiation you take. But if we have the astrophysical evidence that we can see the globular cluster in our Milky Way, which is like 11 giga-year. So if you consider that all today is 100% matter, this omega m equal to going to 1, then you get a situation where daughter is older than mother. So a globular cluster is older than the universe itself. So there is some problem there theoretically. So we have to put it, now if you do use that dark energy, like you keep this dark energy term, and you can put like 0.7% of the dark energy, you get a, and this is a plot where you can see that how the age of this is H0 and T0, age of the universe. This is the old plot. I didn't find like a recent plot, but this is a W map bound on the age of this H0 T0 parameter, and you see that omega m has to be around 0.3. So the matter has to be 30%, and the rest is the 70% is something that we don't know. To give you an age of the universe which is older than the globular cluster. Otherwise, you are in a problem. So this is one evidence that we have some exotic component in our universe. And the most profound discovery of accelerated expansion of the universe is come from the supernova. And supernova is a particular phase of life cycle of a star. So when a stellar nebula form an average star, from average star it form a red giant, then a planetary nebula, then it become a white dwarf. And the other branch, you can have a massive star, very massive star. From there it becomes red supergiant, and from red supergiant it cannot then once it burn its fuel, so it cannot hold the gravitational collapse. Yeah? So then there will be an explosion. It's like a shock wave from the neutron core, I think, that will blast. And there will be two states for this. Is you can form either neutron star or you can form a black hole here, depending on the mass of this progenitor. But there are many different types of supernovae, and they are classified from their spectroscopic observation. So if you observe a supernova which has a hydrogen line, so it becomes type 2. And if it has a no hydrogen, then you can have a sub-branch when you have a silicon and there is no silicon. So, and then you get all these 3 different types of supernovae. And the one without no hydrogen and with silicon, that gives us the type 1A supernovae. And type 1A supernovae is particularly interesting to cosmologists because they can be considered as the standard candle to measure the cosmological distances. And out of these 4, these 3 are like core collapse. The core actually collapse to either to a black hole or to a neutron star. But for this one, the star is completely obliterated. It's like complete explosion. And this is useful for us to observe the cosmos. And what happens generally, the type 1A supernova happen when in a binary system. When you have like 2 white dwarfs or some other, 1 white dwarf and some other star. And there is accretion happening. So the accretion means from another star, the material is coming to the accreting and coming to the white dwarf. And the mass of the white dwarf is increasing. And when it's increased, it touches the Chandrasekhar limit. So this thermonuclear explosion happen, and the whole star is obliterated. So this phenomena of like the mass is increasing and it reaches a threshold and there is a boom, and that gives you somehow a astrophysical tool for us to use it and standardize it for observation. And this is why using this to the discovery of this type of supernova discovery of the accelerated expansion of the universe happen. And what we see for a supernova is like we see their light curve. Light curve means a supernova happen, and then we can see the absolute magnitude or the luminosity of the supernova, how it is decaying over the days. Yes. So as you can see, different kind of supernova. The black one, this is type 1A. So the different kind of supernova has a different decay profile. Yeah, the luminosity decay differently. For the type 1a supernovae, you can see several type 1a supernovae, and their light curve is, look, they behave like a very similar way, correct? And only the magnitude is different, and this magnitude difference is so we cannot use this for the observation, because these light curves are not calibrated. So the different supernova has a different, even the profile is same, but they have their magnitude is different. So this was a problem when people are observing supernova. But there is in 1993, Mark Philip gave a relation which is like this: MB max. MB max is the absolute magnitude max in the blue filter, I think. So then he gave this kind of a correction terms, where you need to check the supernova how from the maximum amplitude how it decay within the 15 days, and you get a correction term here. And when you put this correction term and you correct the previous plots here, you use this correction term and you see this nice plot, everything is on a line. Yeah, everything matches for all the supernova, type 1a supernova, and that makes this to be a standard candle. Now we can actually see a supernova, and we can impose this relation, yes, to find the luminosity distance. Or yeah, so this is how the supernova. After this relation comes, then there are a lot people started to think applying supernova observation for finding out the Hubble constant. And for the supernova observation, we need to know two different magnitude. One is called apparent magnitude, and another is absolute magnitude. Apparent magnitude is like the brightness as observed from the Earth. So brightness of a star which is as observed from the Earth, and the absolute magnitude is suppose there is a source and you bring it at a distance, take it or bring it to a 10 megaparsec distance, and that gives you the absolute magnitude. And when the apparent magnitude is more negative, and then the star is more bright. And the opposite for the absolute magnitude. Absolute magnitude, it is like when it is decreasing, so the star is becoming dimmer. So this concept of this observation, this is astrophysical stuff. So if you want, you can go to any book for more details. You can arrive at a distance which is this is out at a relation which gives us the relation between the absolute magnitude and the apparent magnitude and the luminosity distance. And why this 5 and 25 comes? So I just give you idea. You can go check any book. It's like historically, I think people in Greece, they consider the brightest star to be like 5 and the dimmer star to be 1, and then it's a 5 magnitude, and now we keep the same concept and we divide it by 100, so in a log scale. So you will get this 5 and 25. You have to do a bit calculation, yes. And now if you know the definition of DL, no? This is the definition of DL. And as you can see, now you can connect your supernova observation to your cosmology, because DL actually has the information about your age. So this is the plot where we saw different like the absolute magnitude, mu, apparent magnitude, I think, for the supernovae, and we try to fit it with our cosmological model. And when we try to fit it, you see the red one is all cosmological constant, like 100% cosmological constant. The blue one is 100% matter, and the green one is 70% cosmological constant or dark energy, and 30% is matter. So even in by eyes, without doing any statistical analysis, you can see that the green one is fitting the data better. Yes, you don't need to do any statistical analysis. But if you want to write a paper, you have to do it. Yes, you cannot claim by eyes. Okay, so these are the two more like the most recent compilation of the supernova data. One is the Pantheon Plus and Pantheon Plus SUS. Pantheon Plus SUS is it has the calibration from the Cepheid star, I think, so it's like you have supernova. The host has also a Cepheid, and so you can measure the distance to the Cepheid, and you can actually calibrate it. And you have the DES year 5, which is having like around 1635 supernovae, and it used machine learning to detect these supernovae. And so these two are the most recent calibration, most updated compilation of the supernova. Yeah. Do you have any question before I? Oh, break? Yes. Oh, yes, a break time. 10-minute break. Oh, yes, please.
Like back to when we define the absolute magnitude, where we have to fit to that distance at the 10 per second.
Yes, you have to take the star to 10 mega.
Why we have to this number?
We have to do this number.
Yes, why to be 10 per second?
Yeah, it's a convention. It's why 10 megaparsec.
Also because 10 megaparsec you don't feel cosmology. It's purely
It's purely
the standard.
Standard, yes. Yes. No, 10 parsec, not megaparsec, sorry, 10 parsec.
The 25 just
Yes.
multiplying divided by 10 to 5.
Yes.
But the 10 parsec is made as a pivot scale on which cosmology doesn't play any role.
Yes.
Some star can be very large, and then when you say the distance of the parsec is defined by the astronomical unit to the star with 1 arc second, but then some star is very large, and you don't really know what is the boundary of the star, the surface of the star. So you don't know how close to the surface of the star you can measure. So then you just assume that's the center of mass of the star, and then move away 10 parsec, and then make that as a convention. Because if without convention, it's very uncertain which length scale that you want to use. Just that become convention.
Is there any question from the part 1? No? Okay. So now we will be discussing about another cosmological what is happening? Okay. Another cosmological observation, which is the cosmic microwave background. Probably all of you know the basic of cosmic microwave background, which is like the relic radiation from the very early universe, when the universe was in a plasma state, high energy plasma, so the photons were tightly coupled with the baryons, and it was like a very opaque universe, and the universe was expanding at the same time, so the photons were losing energy, and at a time the photon can travel freely, and this gives us a background relic radiation background, which is in the microwave length, and we call this the cosmic microwave background. And as Shane was saying that this is the temperature fluctuation in the CMB on the CMB sky. It is in the fluctuation is of the order of a million, and otherwise you can consider it to be the whole map to be homogeneous, there is no variation. And it was discovered by the Penzias and Wilson, and they got Nobel Prize in 1978. And this you probably know about the funny story about the CMB. I think the PG they killed some when Penzias and Wilson was observing. I think they have a bell-shaped like radio antenna, and they are observing something, and they get the background noise everywhere. And at the beginning they thought maybe some pigeon is doing it. So they clean the pigeon seed and kill some pigeons also. So, and that was like the funny story about the discovery of CMB. And the CMB gives us a surface which we call the surface of the last scattering. Yeah? After that, we cannot see the universe, because it's like when you go in a cloudy day, you go and see the sky, you can see only the I should say bottom of the cloud. Yes, you cannot see anything beyond that. Yes, so this is the similar situation here. And this CMB to find the CMB anisotropy, it is quite complicated. You cannot do it in the background level, and you have to go to the perturbation, and you have to use this called Einstein-Boltzmann equation, where the Einstein-Boltzmann equation at the curved space-time, and you have to solve it for all the species of the universe, and then you can calculate it. And this is done. You have to do it numerically, and this is generally done by the codes like class and camp. And after doing that, you can get this is the CMB power spectrum, and you can get something like you can plot this with respect to the multipole, and you will get this kind of this plot. And these are the acoustic oscillations of the CMB. And this shows that how these plots can change when you vary the different cosmological parameters. Here you are changing the total, omega total. Changing omega total change this peak. And omega total for greater than or less than 1 gives you the curvature, positive or negative. So this is sensitive to the curvature of the universe. And this is how much dark energy or matter you have, and this is how much variance you have, and this is I think this is how much matter, this is how much dark energy, and this is how much variance you are having. Yes, please.
Is this when you vary the omega lambda, for example, omega lambda, omega baryon, so the other part of this contribution are fixed or
fixed that.
But then it have to be 1 in total or not?
1 in total, but it depends on if you have a curvature or not. But if you fix it to be a flat case, then it has to be 1, and then.
I wonder if you change omega baryon h square to some value, and suppose you increase it, it might take the other contribution away from like omega lambda or omega m, something like to add it up. But then it doesn't say on the.
So here the Friedman constraint had to be satisfied, whatever you do. So omega m, omega baryon, radiation, curvature, total has to be 1. So that has to be satisfied. And when you are trying to find the sensitivity of 1, you are keeping the other fixed. But I understand that when you vary 1, other will vary. Yes. So, and then yes, and this peaks actually tells us some more details about the universe. Like the first peak gives us spatial curvature. They are sensitive to many things, all the parameters, but more sensitive to spatial curvature. This is more sensitive to the baryon density, and this is dark matter, and this is the damping tail. Like we call it silk damping, when the due to in a photon, these happen. These oscillations are like damped because of the diffusion of the photon and the random walk of the photon. And now, as I say, to find the CMB anisotropy, you need to solve the Einstein-Boltzmann equation and the perturbation. But if you want, if you don't want to do that, you can use the compressed CMB. So in that way, you find out these two. One is called acoustic scale, and another is shift parameter. Changing these two parameters actually change the geometry of this CMB power spectrum, and then you can use the like this the observed value of this LA and RZ. So there is no direct observed value, but you can estimate this value using different numerical techniques to put a similar CMB-like constraint on your model without solving the Einstein-Boltzmann equation. So this is the acoustic scale. It's like 1 plus Z star, and the Z star is the distance to the CMB surface, and then Z star is the, I think, no, this is maybe just I think CMB surface maybe, and then R drag, I think drag surface, yes, baryon drag surface, yes, and 1048. Yes. Is
the drag direction where the photons from the stage. So we essentially for the standard rule BAO.
Yeah, it's BAO scale actually.
It's slightly different from the combination.
So this is like a fitting formula. You can do it completely numerically integrating it, but this is like a fitting formula you can use to use the compressed CMB, not going to the whole detail of the CMB data. And you can constrain your model. And this is from the Desi DR2 paper, Desi data release 2 paper from 2025, where they use this, not exactly this approach, but a very similar approach for compressed likelihood. They use the theta s instead of R and LA. Theta s and the small wb means omega b h square to get this compressed VAB. And this is what they say that this is for late time, you can see it's like quite accurate, the original Planck and this compressed Planck. So in case if you have a model, you want to use the CMB constraint, you can use this this likelihood. Any questions? Or? No? Okay. This one? This one are like, what shall I say? It's like, this is the MCMC, and the MCMC have the walker, and this is like walker is walking and got some region which might be not, it's called, can we call it, it's called burnout, I think, burnout region. So he's asking about this part, what happened to this part? Why it looks so ugly? Is this?
Okay, so the compressed CMB has less data points.
Yes.
So overall, it will have less constraining power. So you would expect that the regions to be larger than the full CMB data, actually. So it's not so surprising. But if you only consider omega m h naught, those parameters seems to be enough. But for other parameters, honestly, you have to go beyond that. This is what it says.
Yes. Thank you. Yes, and now the CMB could have polarization because of the Thomson scattering, and this is like going to be that very like upcoming observation in maybe next decade, I hope. And it could get like two different kind of CMB polarization of CMB photons. One is the E mode, which is the curl-free mode, and another is the B mode, which has like curl. So this is created from the scalar perturbation, and this is created from the tensor perturbation. And E mode is already observed, and this B mode gives us the signature of the gravitational wave, primordial gravitational wave. So it's going to be like, yeah, we hope people will detect it. Yeah, any question? No, I will move to the BAO. Okay. Again, this graphics is from Gemini.
As long as CMB mode is not detected, does that mean inflation is not yet confirmed? Although it's a successful paradigm, but it's not yet confirmed.
I think there are other indirect observations for the inflation. This will be a like reconfirmation of the.
Like even without the CMB.
Okay, so there is another interesting phenomena, observed phenomena, which is called the baryon acoustic oscillation. The oscillations you see in the CMB power spectrum, you can actually see it in the large-scale structure. And what happened when you have a kind of universe which is a hot like plasma? It's like soup of photons and baryons and interacting tightly with each other. And you also have the dark matter. Dark matter is sitting here, and it is actually trying to collapse this fluid. And when it try to do it, this will generate the radiation pressure. So the baryon will try to fall to the dark matter potential, and then the photon, because of this compression, the photon will have the radiation pressure. So the baryon is trying to fall, and the photon is trying to like expand it. So it's like a spring. Yes. So there will be some two opposite forces, and you get an acoustic wave traveling through that plasma. And in that time, in the universe is also expanding. And when during very close to this recombination, when the photon travel freely, you will get like the baryon is left as like a cell. And you should be able to see this in the currents when you observe the large-scale structure currently. You want? No? Okay. So this is like a prediction, and yeah, this is the same thing what I told you. Now this is like from Who website. I get a very nice animation of it. So consider all these dark matter, gas, photon, neutrinos, all are there, and they have the same density contrast at that time. So that their amount of perturbation is same. Now if you make them evolve, so you see that this is like Z is like 1400, 14,433 years. So dark matter remains same there, and because you have the radiation pressure, and this is the tight coupled photon and the gas. The gas means the baryons, and this is the neutrino. And neutrino is not interacting; it's just decay. The profile decay quickly, and this one is moving outward, and then it move outward, and the universe is expanding, and neutrino is also decaying faster. And at this point, this is the R drag, Z drag, I think, the drag epoch, when the photon is not interacting with the baryons tightly, so the photon start to get separated. And as you say, the photon is like photon travel, but you get a bump of like a baryon. And over time, even the baryon fall off back to the dark matter potential, because the not photon, baryons fall back to the dark matter potential, but still you will get a bump here. If you calculate the correlation function of the galaxies today, you should see a bump here. And yeah, oh, this is there was an animation. I think it's not working. I don't know why. Okay, anyway, so this is the animation of the same thing. So you should see a bump here. And when we see the we measure the correlation function of the galaxies from the first it was detected in SDSS, Slogan Digital Sky Survey, and you see a bump here exactly as predicted in theoretically. And also to fit this data is fitted when you have like a 70% of dark energy. The fit is better when you have dark energy. Yes? So this is another proof or like evidence that the accelerated expansion of the universe. Yes, and what do we measure in the BAO observation? So there are like this line of sight measurement when you see how far is the sound horizon from your line of sight, or you can see it in the transverse direction, and you define this in terms of Hubble parameter. You can get it, and you can get it in terms of the angular diameter distance also. And this is this is from the current Desi observation. So you can write that this drag epoch RD to be like from infinity to the ZD. ZD is the redshift where this the photon decoupled from the baryon, and they travel freely. And then you have to do this integration numerically to get the proper RD. But there is a fitting formula for RD. If you keep your the recombination physics to be standard, you are not changing something there, but then you can use this fitting formula to find out the value of RD, which is like 147.05, and then this is the standard value of omega B, and this is omega BC is the this is baryon, and this is I think dark matter I think, and this is the N effective, and these are the standard value and the ratio how much you differ from the standard value, and you get this fitting formula. And from there you can actually consider this you can measure the DM, which is transverse co-moving distance, and then you can measure the line of sight direction, and you can also measure the angle average distance. Angle average distance is measured when these two distances have a high signal to noise ratio. So then you go to there. How much is the time? Okay. Yes. Now we know that from the observation, I will go a little bit. Tomorrow, Antonio will go more deeper in this direction. Yes. And there are other observations which we use for cosmology, like a TRGB observation, like tip of the red giant branch, and there is like gamma ray burst. All those things you can find the Hubble parameter from the current value of the Hubble parameter. And but now if we try to know what is causing this accelerated expansion of the universe, the most simple but most observationally still now preferred is the, I should not say preferred now, it has changed, but still it's still preferred, and without any what shall I say, putting much complication to the theory, is called cosmological constant. And cosmological constant was introduced by Einstein in 1970 to find a static universe. At that time, people used to believe that the universe is not evolving, it's static. So if you have only matters, so you cannot have a static universe. And then you need something which can have like a opposite behavior of gravity to get a static universe. So he put this lambda CDM, lambda, and he tried to get a static universe. But what later it find out that the solution he got is it's an unstable solution, and either you go the universe collapse or other it expand. So that's like an unstable point. And when in 1931 Hubble discovered the accelerated expansion of the universe, Einstein abandoned his idea and he said this is like a greatest blunder of his life. But it is truly not, because in 1998, when we discovered the accelerated expansion of the universe, cosmological constant came back as the natural choice for explaining this accelerated expansion of the universe. Yeah. So this is like, how you can put in Einstein equation the cosmological constant, and once you put it, and then you can vary it. From this action you can vary it and you can get back the Friedman equation, but now you get back with the cosmological constant. And as you see that what Einstein was trying, that this has to be greater than 0 to make the universe expand, this has to be less than 0, less than this quantity to make the universe collapse. But if you get an equal sign, so then you get a static universe. But even he abandoned this idea, but we can use this, the first option, to make the universe expand with acceleration. And after that, lambda as the dark energy and cold dark matter as the dark matter become the concordance model or the standard model of the cosmology. And it has been verified by several observations. Till now, it is very successful model, and it can fit the data from CMB very precisely, as you can see here. This is from the Planck 2018 result, and yeah, these are the like some posterior plots. Those who know, they understand it. From using the Planck data, you can get all these plot. You can go to the Planck 2018 paper for more detail about these plots. And but even lambda CDM is the best model till we have. It suffers from challenges from both theory and observations. And one of the theoretical problem with the cosmological constant is the cosmological constant is this, that the observed value of the cosmological constant is low, like 120 times, 10 to the power 120 times compared to the theoretically calculated value. And if you go to, as far as I remember, go to some string theory theoretical model, you can reduce it to 10 to the power 70, but still it's 10 to the power 70. And this problem arises when you try to tell that cosmological constant is the energy associated with the space itself. And if something associated with space from quantum field theory, we know it has to be the vacuum expectation value. And if you relate it with that, you come to this cosmological constant problem. And still now we don't know if that analogy for me is true or not. We can map it to that or not. But maybe I will now stop now, and maybe for the next I will finish.